Hi everyone. So some of you asked that we do a review on the Fourier series and how can we extract harmonics and the fundamental components from Fourier series. So I'm just going to do a quick review of that. So if we have a Fourier series expansion period, Fourier series expansion for periodic functions, and we want to write that, we can write that as x of t here and equals 1 over 2 a naught, and this a naught is a DC function plus sigma of some cosine and sine values multiplied by an and bn, which are constant values, and this sigma goes from n1 to infinity. Okay, so this is the Fourier series expansion for a periodic function. Now when you want to write this Fourier series, the key important things to find is a naught, an, and bn. And how do we find them? We find them based on these three formulas down here. Okay, so a naught is basically the average of the signal here. So you're taking an average of the signal, and an can be found from this equation here. So you just integrate 2 over time period and then integrate of 0 to time period x of t, which is your function time cosine of n omega t dt, and then bn is the same thing except that it's sine of n omega t dt. Okay, and important thing to notice is that we have n omega t under the cosine and sine here, and n goes up with the sigma, and omega is the frequency of the periodic function, and which is basically 2 pi f, and f is the frequency of the periodic function, or we can write it as 2 pi over the time period. Okay, so this is one way of representing a Fourier series. If you look here, this is an cosine plus bn sine can be written as capital An cosine of n omega t plus some phase angle, phi n, right? And plus 1 over 2 a naught. So this is another way of actually representing a Fourier series of periodic function, where a naught is exactly the same as what we had as capital A naught is the same as small a naught, because this is the DC component, right? So this one doesn't change. And but now how do we find capital AN? Capital AN can be found from root square of this an to the power of 2 plus this bn to the power of 2. Okay, and phi of n can be found from arctangent of b of n divided by a of n. Now why do I do that? Why do I change it into this format? Because it gives me a DC value plus the addition of some cosine and each of the cosines are at one frequency. So frequency omega is the first one, and then the second one would be 2 omega t, and then 3 omega t, whereas here we had a frequency cosine of omega t and sine of omega t, and then we had to add them into each other. So basically it's another way of representing it. Okay, now if we open this up, so x of t is equal to 1 over 2 a naught plus n equals 1 is a1 cosine of n here is 1 omega t plus phi of 1, right? And then plus okay, plus a1 cosine of omega t. This form here, when n equals 1, is called the fundamental component of the signal, or of x of t. And then I have a2 cosine of 2 omega t plus phi 2, then a3 plus a3 cosine of 3 omega t plus phi 3. You get the idea to the infinity. So everything from n equals 2 to infinity is called the harmonic components. So all of this will be harmonic components. So this, when n equals 2, this would be our second harmonic. And when n equals 3, a3 cosine of 3 omega t plus phi 3 would be your third harmonic. Okay, so these are some definitions that some of you were asking. Now, some of the things when you want to find an and bn, this might make your work a little bit easy. So if x of t is an even function, b of n would be 0 for all n. If it's an odd function, a of n would be 0 for all n. And if it is a half-wave symmetry where cosine of t is equal to minus cosine of t minus capital T divided by 2, where capital T is the time period, n and bn would both be 0 for when n is even. Okay, so this is the basic idea. Now let's try to solve this example for this square wave with magnitude a and minus a. So find the Fourier series expansion, nth harmonic component, RMS component, RMS of the nth harmonic. Okay, so for as you can see here, this is an odd function, and when we have an odd function, what did we say? We said a of n is 0 for all n. So I know that a of n is 0, so I don't need to calculate this. First of all, I'm going to write the Fourier series expansion, right? So I need to find a of 0, a of n, and b of n. Because it's an odd function, I know that a of n is 0, and then a of 0 is 0 as well. So the only thing that I need to find is b of n in order to find my Fourier series. And okay, so but there's another thing too. So this circuit has a half-wave symmetry, and the value that you have here is minus the value at t over capital T over 2 squared further ahead in time, right? So that's why it's half-wave symmetry. So also b of n would be 0 for all n even, and we're going to see that in the formula as well. So b of n is equal to, this was the formula that we could find it from, right? So 2 divided by capital T integral from 0 of t x of t, which is our function here, sine of n omega t dt. So from here on out it's just math. So I plug in, so I divide the integral from 0 to the end of the time period into two parts, one here and one here. Okay, so basically this part and this part. So from 0 to t squared, and then x of t is just a. I took a out of the parentheses, out of the integral, because it's a constant value. And then from t squared to t of minus a, and I took the a out of the integral, sine of n omega t dt. Now so this here and this here are equal, so I just said this is equal to 2 times the first integral and try to solve that. Okay, so 2 times 2a divided by t here would be 4a divided by t, and so integral of 0 to t square sine of n omega t, and then you can find it as this guy here. This is a multiple for a, and when you find it, you'll end up with when you do the calculations, you end up with 2a times 1 minus cosine of n pi divided by n pi. So when n equals, when n is even, so you would always end up in here, and cosine of n pi would be 1, and 1 minus 1 would be 0. So for all n even, b of n is 0, and we also said this before, right? From the half-wave symmetry, we said b of n is 0 for all n 0. And when n is odd, cosine of n pi is -1, and this would be 2. 2 times 2 is 4. 4a divided by n pi. So now, if I want to write my Fourier series expansion, this would be it. And I don't have a naught, I don't have a n. The only thing that I have is b of n. Oh, and sorry, this has to be, so n has to be odd, right? So 1, 3, 5, you get the idea, to infinity. So, and so what's the fundamental component? The fundamental component is when n equals 1. So 4a divided by pi times sine of omega t is the fundamental component. What's the nth harmonic? Harmonic component. It's the nth, whatever value as the nth sinusoidal, right? It's going to be 4a divided by n pi sine of n omega t. This is going to be my nth harmonic component. Now, what's my RMS of the fundamental? Since this is a sinusoidal waveform, the RMS wave value would be just divided by root square of 2 here. And what's the RMS of the nth harmonic? So xn RMS is going to be, again, so because this is a sinusoidal waveform, only we divided by root square of 2. And if you see, that's actually the value of the first harmonic divided by n, which is we're finding for the nth harmonic here. So that's a quick review of that, how to find basically the relationship between the harmonics, fundamental components, and how to find the Fourier series.